Everybody to the middle session. I'm rather tempted just to say here's Bill. However, I'll give a slightly more formal introduction. This is Professor William F. Rosenberger from the University, George Mason University in Virginia. Thank you, Bill.
Thank you. And thanks to the organizers. Very happy to hear so many randomization talks. I used to be the only one at these conferences that ever discussed randomization. So heard a lot of them. I'm going to go back to the basics, as I think Dieter will be doing after my talk. So I'm going to talk about some typical randomization procedures and what their behavior might be in small clinical trials. So when I say small clinical trials, okay, so here's the table of contents. When I say small clinical trials, these can be as a result of doing a clinical trial on a rare disease. And rare diseases have a low prevalence. There are 6,000 to 8,000 rare diseases that affect 30 million people in the EU, and I know all of this from Dieter and the IDEAL project. About 50% of these rare diseases are in children, 80% have genetic components, and 20% have other causes. And so recruiting sufficient subjects is sometimes difficult. Appropriate subjects may be spread thinly. They may be spread across many countries or many regions. And because many of these diseases are life-threatening, alternative therapies may not exist, and there may be ethical imperatives to determine to try to maximize the number of patients on the experimental therapy. So some of these trials can be quite small, and I think Dieter is often saying parallel trials of size 8. I'm going to talk about slightly larger trials, maybe about size 50. One common approach that I've seen more and more often in protocols in the US at least is to have a 2-to-1 allocation on some of these rare diseases and pediatric diseases so that 2/3 of the patients receive active therapy. There are some problems with that because, first of all, it increases if you just do a simple homoscedastic normal assumption, that increases the sample size by 13%. Another problem is that the experimental therapy might actually be harmful, in which case 2/3 of the patients are being assigned to a harmful treatment. So there are other approaches. Some have used crossover designs, but it also may be impossible to withdraw a patient from the experimental therapy if they've been randomized to it in the first stage. Think of chemotherapy. You can't just withdraw chemotherapy in a second stage. So another approach is to have a 2-stage trial where only the first stage is counted, but on the second stage, everyone gets the experimental treatment. So I've seen all of these designs in protocols. I don't really like any of them. And sometimes the experimental therapy is not effective or toxic, so just blindly increasing the number of patients assigned to it doesn't seem like a very good idea. Now, I would love to then say that the solution to this is response adaptive randomization, which we've heard about. And in some cases it might be, but Franz and I and Dieter and others are working to see if in small clinical trials, these procedures that tend to asymptotically do good things may not really do all those good things in smaller samples. Some rare diseases are more homogeneous across doctors, clinics, and borders, so maybe we don't need to worry about stratification by site as much. Also, patients may all have the same genetic marker for a rare disease. So some of the considerations that we often think of in designing a clinical trial may not apply. But the typical benefits of randomization are the reasons we do randomization: comparability on underlying covariates, unpredictability to minimize bias, These results are largely asymptotic properties, so it's important to look at them for smaller samples. And then I would say, although many people apparently disagree with me, that my very last point here that was there a minute ago, where'd it go?
Push the other button.
Which one? That
You're
one?
going forward.
Okay, all right.
Yeah,
Sorry.
that's fine.
There it is. Okay, so as I'll tell you later, standard homogeneous population models based on IID samples that are invoked for inference may not be appropriate for small clinical trials. I would argue they're probably not appropriate for large clinical trials either. So basically what I want to do is go back and look at some of the standard procedures that are used for small clinical trials, and I'm going to be interested in my criteria of balance for efficiency purposes, comparability on unknown covariates, and predictability, and then I'll talk about randomization as a basis for inference. So the standard clinical trial paper, because I referee a lot of them, will have about one sentence in them, and often it says, randomization was performed using Excel. That's a typical statement that's made in many clinical trials papers, and then there's not a single other comment about randomization in the paper. So I'm going to talk about different randomization procedures and some of their properties, and we might find some surprises here, or maybe not. So this one isn't used very often. It's just common coin tossing, complete randomization. The probability of assignment's always 1/2. This is the most unpredictable type of randomization sequence, but there are potentials for large imbalances both at the end of the trial and midway through the trial. And also you can have certain runs. Since we're only doing a clinical trial once, we'd like to eliminate the possibility of weird types of sequences. So for that reason, we often use a restricted randomization procedure. So in a restricted randomization procedure, this phi j, which is the conditional probability of assignment on A, it's based on the previous assignments. So it's a conditional probability conditioned on the first j-1 treatment assignments. And usually the conditioning is done on the random number of patients that have been assigned so far to A. Is there a, I know I'm the 37th person to ask how to use this, and I should have paid attention to how they did it. Show me how to get a little pointer. Oh, I'll use this. I'll be like Fedorov. Oh, beautiful day outside. What? No, I'm going to use this. Okay. So, and we have this metric, which is the imbalance metric. So we want to know the difference between the treatment A number on treatment A's and treatment B's. And as my doctoral student number 6 said yesterday, to be a valid restricted randomization procedure, the unconditional probability of A must be 1/2 for all patients. That's he's not here today, so I forget what he called that property. The APR, it's some acronym.
ARP.
ARP, thank you, Rosemary. Force balance procedures, we don't typically use these except in blocks because we don't often know the exact number of patients that are going to be in the clinical trial. But if you wanted n over 2 patients to be on A and n over 2 patients to be on B, there are 2 ways of doing it. One is a random allocation rule. You can just think of an urn that contains n over 2 A balls and n over 2 B balls, and you just keep drawing without replacement. The second possibility is a truncated binomial where you just flip a coin until one of them reaches n over 2, and then you assign the tail deterministically to the other treatment. So there are other fixed sample size force balance procedures. Timofeyev gave one yesterday for unbalanced allocation. This is the Berger. I don't know if I should, like him, I don't know if I should mention the second author because I'm going to criticize it later. Student number 2, Ivanova, maximal procedure. This is the random allocation rule, but basically you remove all sequences from the allocation rule where you exceed some imbalance parameter b, and then you rescale so that all randomization sequences are equally probable. So there are blocked procedures, and these are used in 90% of clinical trials. Permuted block design, blocks of even size 2b are filled. They never tell you how they're filled, but since I'm a randomization-based inference person and I use the randomization procedure in the analysis, I always need to know how the blocks are filled so I can replicate the randomization procedure. The maximum imbalance is half the block size, and the only possibility of a terminal imbalance occurs if the last block is unfilled. Because there are a certain number of deterministic assignments at the end of each block, many people have decided that they want to randomize the blocks. So a random block design, this is never defined how they actually do it in these papers, but if you want to formalize it, you could do something like saying we have a discrete uniform distribution on 2 blocks of size 2, 4, 6, 8, up to some maximum block size, and we randomly generate the block and then fill it using either the random allocation rule or the truncated binomial design. Hadamard randomization, this is Rosemary Bailey's paper. So a Hadamard matrix is a matrix of 1s and 0s in which 2 different rows have the same entries in half the columns and opposite entries in the other half. And in that paper, they give us a special example of size 12, and then she removes 1 row, doubles the rows, switches the 1s and 0s, and creates 22 equiprobable randomization sequences. I like this design very much, but I'm afraid that I would need Rosemary there to tell me how to do it. That's my only problem. And Rosemary isn't in SAS, so that makes it more complicated. Proc Rosemary, maybe. Okay, so efference bias coin design. So these are adaptive procedures, so you get a probability p greater than 1/2 of assigning the treatment that has the fewest assignments thus far. So most people are familiar with that one. And then there are modifications of efference bias coin designs that tend to do a little better. The accelerated bias coin designs of Professor Giovagnoli there. And this is a scaling, basically, of the difference metric with a parameter A. So I'm going to compare some of these designs later. And Smith's is a different flavor of that. It's a scaling of the difference metric. So you randomize with the probability that depends on the number of patients assigned to B thus far. And again, there's a scaling parameter rho. And these things reduce to special cases. Rho equals 0, it's complete randomization. Rho equals 1, it's a 1978 Ways design. And if rho equals 2, it's an Anthony Atkinson design. So some of these are generalizations of these other procedures. And then you can have the Ivanova type of constraint. You have an imbalance parameter like the maximal procedure. So maximal procedure is a random allocation rule with a reflecting barrier. You can also have a reflecting barrier on complete randomization, which is called the big stick design, and that's a Jeff Wu design. And then the bias coin design with imbalance intolerance by Chen is basically efference bias coin design with a reflecting barrier. You can put a reflecting barrier on any of these. You can get compound criteria, as Professor Giovagnoli mentioned on Monday. And so there are an infinite number of designs that you can come up with for these things. So let's compare the procedures first with respect to balancing properties. Let me just show you the difference of these procedures. So there are some of these adaptive procedures that all 2 to the n possible sequences are possible, such as efference bias coin design. Complete randomization, these 2 to the n are equiprobable, but the efference bias coin design is going to restrict the probabilities, the large probabilities, to be somewhere in the middle. So, but you can still have a positive probability of getting an extreme result there. Then we have these designs with an imbalance with a reflecting barrier. So you can never go beyond, this is a reflecting barrier of size 3. So you can never go beyond the border here of size 3. It always shoots it back with probability 1. And then there are the block designs which tie everything down after blocks of size. In this case, my blocks are size 6. So those are the 3 flavors of designs that we have here. So balancing properties, many of these you can derive exactly, but these are simulation results. You see the simulation error because complete randomization, that's exactly 50. And you can see that the block designs, the only imbalance you can get, this is the variance of the imbalance, the only imbalance you can get in the block designs is if the final block is unfilled. And you can see the balancing properties of these others. So all of these adaptive procedures are fairly similar. Comparability on unknown covariates, one of the great properties of randomization. One of the reasons we use randomization in clinical trials is because it tends to balance with respect to any unknown covariate, including those that may be correlated with the patient outcomes. This is an asymptotic property. It's usually proved with a Chebyshev bound. And so I wanted to see how it does in smaller samples. So we have a stream of covariates that are just IID normal, and then we have a drift over time, and then we have an autocorrelation. So let's see how these procedures do with that. This is the probability of an imbalance defined by the difference in means exceeding some threshold. And you see all of them do a great job if we have normal 0-1 IID covariates. Not all of them do a good job when you have time trends, and in fact the better ones are the Giovannioli type ones and the accelerated bias coin design and the bias coin design with imbalance intolerance. And then for autocorrelation, again, the better one tends to be something like Smith's design and Giovannioli's design down here. So all the procedures work as intended for the IID sequence. And I'm not going to talk about Stevenson's philosophy now because I don't have time, but it is interesting. And Stevenson's not here, so I don't need to reference him today. So the second great property of randomization is that the sequences tend to be unpredictable. Only complete randomization is really purely unpredictable with the probability of 1/2 for each patient. In restricted randomization, the unconditional probability of assignment is 1/2, but the conditional probability may not be. And so we can take a metric of predictability. This has been proposed many times in the literature, comparing the conditional probability of assignment to A versus the unconditional. So a metric of the difference between that and 1/2. So you can just think of the sequence of probability of assignments and compare each to 1/2, take the expectation and sum. And this metric is between 0 and n/2. So best case scenario is complete randomization when it's 0, and then just an alternating deterministic sequence will give you this will be 0 or 1 each time, and it'll be n/2. Others have proposed different metrics. These French authors define predictability as the proportion of treatment assignments with probability 1. That ignores treatment assignments with probability 0.99, which can happen in some of these procedures. So I think a better predictability metric measures the whole range of values. And I won't talk about Stevenson again. Okay, this is a typo. That should be plus, but these are simulation results for n equals 50, and you can see that this predictability metric is best for the Smith design with rho equals 1, and it gets worse as we go on, and unfortunately the maximal procedure which was actually invented to prevent selection bias, is actually not any better than some of these other procedures. Big stick design is quite good, and Smith's design is quite good. And Hadamard, that's in the 6s. But then what I want you to see is these blocks in particular. This is what everyone uses, the permuted block design. Those are really the worst of all of them. And people say, well, then we will randomize the block sizes and we'll get a much better predictability measure. And it is a little better, but it's not as good as these other adaptive procedures. And that's been found in a number of papers. Predictability and balance are competing objectives. The procedures that are best at balancing are also the most predictable. You think of an alternating deterministic sequence. Complete randomization is the worst procedure with respect to balance, but it has no predictability. The maximal procedure was specifically designed to be less predictable, but it has about the same predictability as the permuted block design with block sizes of 4. The random block design is often used to eliminate predictability, but doesn't, as we've seen. So I can scale these things, and I'm not the first person to do this. Anthony has a paper doing it, and the people from Medical University of South Carolina have a paper that do this. And Alessandra would do it mathematically using a compound optimization criteria. I'm just going to do trade-off plots. So we scale everything on the same axes, which is important, as Alessandra mentioned on Monday. So we can put them on 0, 1 scales and see what happens. So I can only do 2 dimensions in my graphical capabilities. So I'm just going to look at 2 at a time. The first one I'm going to look at is the balance metric variance of dn versus the selection bias metric. And presumably the best procedure would be at 0, 0 here. And you see complete randomization is the best with respect to predictability, but it's the worst with respect to imbalance. Alternating deterministic sequence is the best with respect to balance, but the worst with respect to predictability. And so we really want the procedure that's, if we equally weight the criteria. And we go down here and we see that the big stick design is clearly superior to all the other designs with respect to these 2 metrics. It's the one that's in this bottom quadrant. It's the only one in this bottom quadrant here. So the big stick design wins this. It's going to win the next one too. Oh, I gave the punchline away. Okay. Randomization is a basis for inference. Hard to find anyone that does this. But if you go back to the old days, Cornfield and the great clinical trialists, they always said randomization provides a basis for inference. But they couldn't do any randomization tests because they were too computationally difficult. So a lot of focus was on the asymptotic distribution of randomization tests. Now we can just compute them in 1 second in SAS just by looping through your original randomization procedure. And the FDA calls them re-randomization tests. So the early clinical trialists were aware of the importance of randomization-based inference but had limited computational resources. These days, I can't even find biostatistics departments that teach randomization tests. And if they, some might do permutation tests. Let me just distinguish between what I think is a permutation test and a randomization test. A permutation test will not take the actual randomization procedure into account, and that's what many people argue is an appropriate way to do this. I was always trained that you should incorporate blocks in the analysis, so I'm going to do that in my randomization as well. I'm not going to use a permuted block design and then assume everything was done by complete randomization, although some people would say that's appropriate. Maybe the results won't be too different. The problem is the reference set has a completely different probability structure. If you assume all N2 to the N sequences are equiprobable, so why would you regenerate with respect to that reference set when you've done a block design or something like that, or a restricted design that has a reflecting barrier? And they're particularly useful in small clinical trials where the standard asymptotic tests may not apply, but they're also useful in large clinical trials. So do I have time for this, Linda? Okay. So I think most people have seen this. And so the population model assumes random sampling and populations that follow some homogeneous distribution. And then you get your patients from random sampling, and they follow that IID distribution in both groups. And of course, all of that's nonsense in clinical trials because we don't have random sampling and we don't have populations of patients taking placebos and things like that. So what people do when they use SAS and get their p-values is they invoke this model. They say there must be some unspecified population and some undefined random sampling procedure that gave us our patients. And then we use randomization, which we'll completely ignore in the analysis. And that actually is the only random component in the clinical trial. And then we'll assume these IID sequences. And then they use their t-tests and their other things. So here's what I do, is I say I have a bunch of eligible, consenting, non-random patients from non-random clinics that probably became a clinic because they wrote the best grant proposal or they can recruit the most patients. And they've got a completely non-random set of patients. And the only random thing they do is randomization, and therefore I'm going to use a randomization test to analyze it. So the idea of a randomization test: under the null hypothesis of no treatment effect, the arrangement of patient responses depend only on the way in which they were randomized. So if we were to re-randomize them many times, the treatment effect should not be affected. The only way that a treatment effect can exhibit itself is if the results change when we re-randomize. So an exact test requires enumeration of all possible sequences along with the associated probabilities, which is quite difficult even in the most simple of these restricted randomization procedures. And so the p-value it's really nice because when you teach this to students, you can actually say the p-value is, they can see it's actually the sum of probabilities of sequences that give as extreme or more extreme a result than what you got, which is our definition of p-value, but they can actually visualize this better if they're thinking in terms of the randomization model. So you have some metric, you calculate your test statistic metric on the observed data, and then you re-randomize, and each sequence has an associated probability, and you sum the probabilities of the sequences that give you a as extreme or more extreme test. Only under complete randomization are the sequences equiprobable. In restricted randomization, they are not. So back in the 90s, I think there were some people that were trying to use parallel processing to get the exact distribution, maybe in the 80s. And in the 80s, we were working on, my advisor and I were working on the asymptotic distribution of these tests. But now we just use Monte Carlo stuff, so everything's easy. So I just removed 3 chapters out of the second edition of my book, just got rid of all the asymptotics and said, do this. So, the treatment effect here, anything that makes sense is fine. You can have log rank tests with censoring if you've got survival data. I can even do it, I'll show you in a minute, I can even do it using regression models, adjusted regression models. So any possible outcome you can think of for a clinical trial you can do. You can incorporate sequential monitoring into this. I have a couple papers on that. So we use the Monte Carlo technique. So we just regenerate the sequence a certain number of times, m of them, and then this is a consistent estimator of the p-value, just the proportion of sequences that give you a more extreme test statistic out of the regenerations of the sequences. So the question is, how many sequences are good enough to get a decent randomization test? Here the asymptotics are not on the number of patients in the trial, it's on the number of sequences you're generating. And usually 15,000 to 20,000, this is a theoretical result. So this is a well-founded result based on the size of the p-value and different metrics that you want to, so this between 15,000 and 20,000 usually work. And that takes less than a second in SAS to do. I won't go into that. So the interesting thing is they tend to preserve type 1 error rate even when the population model is misspecified. So here's a simple example. We can do the t-test, the perfect scenario for the t-test, in which the t-test will always be better because it's that scenario, IID normal 0, 1. Or we can put in some kind of crazy time trend. This is a pretty large linear time trend, and the t-test is going to go blah, but the randomization test is going to be perfect. So here's the result. T-test is always better, maintains the size and power. We do a randomization test. This is model 2. This is with the time trend. Notice the randomization test, 0.05, 0.05, 0.05, 0.05. And the t-test, 0.05, 0.18, 0.02, 0. And the power, a little bit less under a time trend than without a time trend. But you still get 90% power for the random block design, 83% power for the big stick design. The t-test is down here, but who cares about the t-test power? It doesn't even preserve the size. I mean, I'm not interested in anything, if it's not going to preserve the size, then it'd be kind of silly to use. So let's do a trade-off plot for type 2 error rate under a time trend versus the predictability of the sequence. So this is another, so here the optimal, for the t-test, 0.07 is the optimal value for the type 2 error rate. So we can't do better than that. So think of that as your origin here. So we want something that's as close to 0 for the predictability metric and as close to 0.07 for the type 2 error rate under a time trend. And again, if you just draw the, if they're equally weighted as being equally important, the big stick design wins again. And how do you do these under, do I have time?
Yes,
Oh.
10 minutes.
Oh, okay. How do you do these with regression models? So basically what we do is we rank the residuals of the regression model. So you could have a adjusted treatment effect in a model. Could be a generalized linear model, could be a survival model, AFT model, could be a GEE model, something like that. Any kind of model you can think of. So under the null hypothesis, the treatment effect's 0, and then the ranked model residuals should be randomly distributed across all possible randomization sequences. So you can perform a randomization test on the ranked residuals. And interestingly, what we found in this is a statistics in medicine paper, and we also have SAS programs that do all of this stuff for any kind of generalized linear model that you might have. You can specify the link function. You can even do survival models with censoring. While the model may be parametric, the inference procedure is completely non-parametric because I'm going to use a randomization test even though I'm ranking residuals from a parametric model. So my colleague who's an expert in generalized linear models calls this a semi-parametric method because he starts with a parametric model, but the thing he was amazed at is he misspecifies the model. I do the randomization tests, I preserve my size. He does his model-based MLE tests, and the size is gone. So even under model misspecification, you can still preserve the size of the randomization tests. So this framework makes possible randomization-based inference for virtually every possible type of outcome analysis that could be encountered in clinical trials. Treatment effects with continuous, ordinal, categorical, time to event, repeated measures outcomes, covariate adjusted treatment effects from any of those outcomes. They could be used as a primary analysis, a complementary analysis, or a sensitivity analysis, along with standard parametric tests, all of which assume that you had random sampling. Now here's what my colleagues always tell me, oh, many times they just give me the same answer, so why should I use them? Well, I'm not even going to answer that question. So for 70 years, clinical trialists have known that randomization reduces bias due to predictability, induces comparability among important known and unknown covariates, and provides a basis for inference. But randomization is often done in a nonchalant, haphazard manner with no consideration for finding the best procedure for a particular clinical trial and ignoring the randomization in the analysis. And you can see why people say randomization was done in Excel in these papers if they're not going to do anything else with the randomization, ever. They designed the trial with the randomization, and then they're going to ignore it forever. Then what do we need to know except that it was done in Excel? In small clinical trials, which may be necessary in rare diseases, typical asymptotic assumptions may not hold. And in fact, this holds for, we have huge multi-center clinical trials with 3,000 patients, and we randomize by clinical center. It's different in each clinical center, so each clinical center is like a small clinical trial, 50 patients, 100 patients. So I've described different randomization procedures, investigated their properties in small samples, and how to conduct randomization-based inference. Thank you.
Questions?
Alessandra.
I have one question and one comment. The question is the following. You were very kind to the ABCD. That's a design that I like for personal reasons. Now, the ABCD is a family of designs because it depends on a parameter. And you've chosen A equal to 10. Is it because it's particularly...
No, it's because in your paper, you suggest that A equals 10 corresponds well to Smith's design with rho equals 5.
Okay.
So, and this is just one simulation of...
So it may...
And also, I could have chosen many different functions because you have a huge class of procedures.
My remark is, when people compare predictability with, when people compare designs with respect to two criteria, one being predictability and maybe another one, predictability is a sort of average, isn't it? An average over M, they usually take some indicators that are not averages, like loss, for instance, which is only measured for one particular step, N. So I'm not questioning your analysis, but it seems to me that we're not actually comparing two homogeneous with, indicators. We're taking non-homogeneous indicators, but maybe that's not important anyway.
Anthony uses the loss function in his paper in statistical science that just came out last year. I mean, I could take various different metrics. The reason I like this metric of the sum of the absolute values for predictability, it's identically equivalent to the Blackwell and Hodges convergence strategy. So it has another interpretation with respect to a physician trying to guess the treatment. So that's why I used it here. But I mean, I could take any kind of, as long as I can scale on 0 and 1, I don't see a problem with doing this. And Anthony does a loss function.
Because all about testing. Suppose you wanted a confidence interval.
Yeah, that's hard. Right.
See if you have a simple additive effect in your model, you can shift all the values by that, and you're testing a different null hypothesis. But something like a hazard ratio, that must get hard.
Yeah, I'm not sure it's even possible. But I'm not saying you should only use randomization-based inference. You can use it as a supplement or a complement to other procedures.
So this notion of predictability, when I was doing randomized block tests, I always made a point of never letting the physician know the block size. So, you know, so there's some period of time. I don't even remember the doctors trying to guess the block size, but not letting them know the block size I thought was a key component to having it be unpredictable. And I don't know how you'd quantify that in
Well, you don't quantify it. I mean, it's blinded. In a blinded study,
But if they know the block size, then you can predict the last one. But if they don't know the block size, they don't know that it's the last.
okay, so here's what I say in answer to all the people who say selection bias doesn't matter because I do
I'm
double
not criticizing.
double
I'm
blind.
talking about this notion.
I say all other considerations being equal, I want the sequence that's the least predictable. Just as a matter of you know, preference. So you can tell me there's no selection bias in my trial. Well, I'll say, well, I'm more concerned about time trends under the randomization test. I'm more concerned with this criteria. I'm more concerned. But all of those things being equal, I want the least predictable sequence. I don't see what's wrong with that.
I just have a couple of comments, Bill, apart from thanking you for a lovely talk. And one of these is this nonsense that people write down, we've got an experiment and we've got a random sample. Do you know anyone who's ever done an experiment on a random sample? So, I mean, exactly, we should kill that one. And the other is, you're talking about, you read papers and it says we did randomization in Excel. I'm afraid I more often referee biology papers than medical ones, and this is what you find. We randomized. No more information. Can you tell me some more? Well, yes, we tossed a coin for the first one and then we alternated. Do you get that in clinical stuff? You get the same thing?
Well, yeah, I mean, one of the things you see quite often, if they tell you what they actually did, which they usually don't, is permuted block with size 2, blocks of size 2, which is basically every other patient is determined. So.
Any other questions? Bill, thank you very much.
Thank you.
Lovely talk.